Welcome back to the scanning electron ion probe microscopy in material characterization. We have been discussing on different scanning microscopic technique. In that in last couple of lectures we have started discussing on scanning probe microscopy, in which physical probe is used to scan the surface to get the surface information or surface topology. In that topic we have begun with scanning tunneling microscope, and in the scanning tunneling microscope we measure the tunneling current between the tip and sample. Today we will discuss its working principle, in particular how the tunneling phenomena works in scanning tunneling microscope and how tunneling current is measured. In order to discuss the tunneling phenomena, or nothing but quantum tunneling, because here it is a microscopic particle of the electrons, let us talk about a solid which is made up of atoms, and if we talk about atoms, then we say it is atomic orbital. If it is a atom, we say it is atomic orbital. Whole atom has a and if we talk about a molecule, then let us say it can be carbon monoxide and 2 atoms. So, we talk about molecular orbital, can be sigma star type of orbital. Then we have solid, we have several atoms comes together. When several atoms comes together, their energy levels will overlap with each other, forming band. It can be valence band and conduction band in case of solid, and we here talk about the solid, and in the solids we will see how quantum tunneling occurs or tunneling current is measured, and in this case also we have density of states, energy, density of states for the occupied states and unoccupied states. And again solids, these solids can be divided into 3 categories as per their electronic properties is concerned, such as solid can be insulator. In case of insulator, there is a large gap between the valence band and conduction band. There is a large gap, normally it is greater than 5 electron volt, 5 to 6 electron volt. We say it is an insulator, and here there is no tunneling of the current occurs. Then we can have a semiconductor, where there is a small gap between the valence band conduction band, which can be used for scanning tunneling microscopy study. It is to be noted that insulating samples cannot be studied by scanning tunneling microscope, but semiconductor, yes, we can use semiconductor or semiconducting samples for STM measurements. Then we can also have metal, where valence band and conduction band overlap, and these metals and semiconductors can be used to examine under STM, scanning tunneling microscope. Now, in case of these solid materials, we know there is a surface, and surface have electronic structure, and if we want to take out an electrons from the surface, then we have to provide the energy, and we know in case of these materials we have a Fermi level EF. It is a hypothetical energy levels at which there is a 50% probability of the electrons being occupied, and if we want to take out an electrons from the Fermi levels, then we need to provide an energy called work function, and work function is denoted by phi. Work function is equal to the energy difference between the vacuum level minus EF, the energy difference between the vacuum level EV. If we provide the energy of this much, then we can take out an electrons from the surface of a solid material. Now, this work function is nothing but a type of barrier for an electrons to cross in order to go to the other side. Like we have sample here and we have tip here. If a electron has to go from sample to the tip, it has to cross a barrier. And here in case of solid materials, we say that let us say work function is the barrier. If we say that this barrier is nothing but a type of a wall, let us say it is a type of a wall, this is the energy, let us say this is x axis, the barrier is, let us say this is a barrier or it is a type of wall barrier. Now, in the microscopic world, microscopic world, and there is another world is called macroscopic world. In a macroscopic world where particle size are quite big, if a particle has to cross this barrier, it has to cross this energy barrier, then only particle can cross. Otherwise, if the energy of this particle is less, then it will be reflected back. If the energy of the particle is less than this barrier energy or wall energy, then it will be reflected back, and in macroscopic world the reflection is nothing but 1 if the energy is less than the barrier. But in the microscopic world, where particles are very small size, or it is called quantum mechanics. When particles are very small size, we say it is quantum mechanics phenomena will come, and here it is a classical mechanics, particle size are very large. Here the particles, even though its energy is less than the barrier height, this is the barrier height, then also there is a probability that these electrons will pass through this wall, and this is nothing but called tunneling. This is nothing but called tunneling, and I can describe, like for example, here this is a barrier or wall, and an wave is going, it has a probability of passing through it, or it has a transmission probability, and this transmission probability T is proportional to e to the power minus beta d. Here beta is a constant which depends on the energy of the particle and the barrier wall, barrier height, energy of the barrier height, and d is the thickness of the barrier, d is the thickness of the barrier. This is about the quantum mechanics. In case of solid, as scanning tunneling microscope is used on the phenomena of quantum tunneling of the electrons, and electrons are the microscopic or small very fine particles. They follows the quantum mechanics. Even though their energy is less than the barrier height, there is a probability of transmission of those electrons or probability of tunneling those electrons via this barrier, even though their energy is less. We can better describe that using the graph here. In the first case, in the left hand case, there is a solid and there is a vacuum. So, particle has a wave function defined as a psi, designated or assigned with a psi. It has a wave function inside the solids, and that will exponentially decay as we go above the sample towards the vacuum level. In case of, if we bring two solids close to each other with a gap of d, and that is called the barrier thickness, then once it crosses the barrier, it will tunnel into the another solid, and the particle wave pass the barrier. Now, as we know, in quantum mechanics, the particles can be presented by the wave function psi. I can write as per the time independent Schrodinger equation, a simple equation we know, H psi is equal to E psi. So, which we can write minus h cross square by 2 m d psi by dx is equal to E psi, that is inside the solid, and if it is outside the solids we can write minus h cross square by 2 m d psi by dx plus b psi is equal to E psi, that is outside the solid wave function, and these have a solution, these equation have a solution, and we can write like here inside the solid I can write let us say psi n, or let us say I would write psi in inside the solid, I can write here psi in, or let us say this is psi 1 and let us say this is psi 2 and this let us say psi 3. This is what the phenomena works in our STM. Psi in can be have a solution like a e to the power I k x plus a prime e to the power minus I k x, and where k will be root over of, if we talk with the solution, root over of 2 m e divided by h cross square. Similarly, psi out outside, or I can here write psi the psi 2 or psi 2, or it is psi 1, we can write b e to the power I k x plus b prime e to the power minus I k x, where k is equal to root over of like 2 m v minus e. Here it will be v is equal to phi, that is work function. So, I can write here v minus e or phi minus e divided by h cross square. This is what the psi 2. Similarly, this is psi 3 inside the solid. So, it has a transmission probability of this wave. So, it is nothing but t e to the power I k x, where k is equal to root over of 2 m e h cross square. So, now what we see here, this is the transmission coefficient t, which can be proportional to, we can write transmission coefficient is t proportional to the power e to the power minus 2 k d, 2 k d. So, here what we see here d is the thickness of the barrier and k is this one root over of 2 m e upon h cross square. So, once an electron goes via a gap, in this case it will be a t, one side it will be a sample and one side it is a tip. Solid can be sample and it can be tip, and then electrons can tunnel from tip to sample or via sample to tip if we apply a potential. So, now what we see, the transmission coefficient of the electrons is proportional to the power e to the power minus 2 k d. This transmission coefficient is nothing but the tunneling current. So, therefore, we can say I tunnel is proportional to the power proportional to exponential minus 2 k d, as I have described previously. K is root over of 2 k, here I can write phi by h cross square, or if sorry, it is not 2 k, k is 2, it is m, here it is m. To m phi, and if we put the value of m, m is mass of the electrons and h cross, that is h by 2 pi, h is the Planck's constant. If we put this value, then it will be point and phi 0.51 root over of, if we take the work function in electrons, then we will have a k is equal to angstrom inverse, where k is equal to 0.51 root over of phi angstrom inverse, this one. So, here remember phi in electron volt symbol with a unit of electron volt, and here phi is the average work function of, this is the average work function of tip and sample. This is the average work function of the tip and sample. So, by putting the value of phi, which is normally 4 to 5 electron volts depending upon the sample and tip, 4 to 5 electron volts, normally k come in the range of 1 to 2 angstrom inverse, that is called inverse decay length, that is also called inverse decay length. So, as you see this k is 1 to 2 angstrom, 1 to 2 angstrom. So, upon changing 1 to 2 angstrom value, we can see that the tunneling current varies drastically. So, important consequence of this equation is that this tunneling current depends on the thickness of the barrier of in this case as in STM, this barrier is nothing but the gap between the tip and sample, because one side we have sample and then we have a tip here, we bring very close and this gap is our barrier. So, electron has to pass this barrier to go from sample to the tip or in opposite direction. So, for a typical value of work function around 4 electron volt in a metal, the tunneling current reduces by a factor of 10 for every 1 angstrom increase in the D. So, when the tip goes 1 angstrom up or go 1 angstrom away from the sample, the tunneling current decreases 10 times. So, therefore, a precise control of the tip sample gap can be achieved in this technique, because the current is changing 10 times. So, thus it is a very good vertical resolution and high sensitivity, it can give very high vertical resolution. And second thing is that that means why I say very high vertical resolution, because if I have a monolayer and monolayer of thickness is in the range less than 0.1 nanometer or couple of angstrom, then my tip has to go up to maintain the same current, or when there is a steps, then what will happen if my tip is going here, my tip is going let us say here. So, we can measure a much higher current here compared to here, much larger change in the tunneling current as the gap changes in the level of 1 to 2 angstroms. That is precisely very accurately we can measure the step height in the scanning tunneling microscope. So, that is what the very high vertical resolution. And second thing, if the tip has a single atom, as we discussed earlier in our STM, the tip has to be single atom, then only we can get the information at the atomic level, then tunneling current will pass through only one atom only, therefore, very good lateral resolution, because atom by atom we can detect and do the imaging of single atoms. So, this is the advantage of this scanning tunneling microscopy by measuring the tunneling current. It is important to know that this tunneling current varies exponentially with the thickness distance between the barrier and gap, and also it depends on the work function of the material, because the k, it depends on the k is in turn related to the work function of the material. So, tunneling current, the tunneling current again depends on the bias voltage and the distance between the tip and sample. I have not so far discussed the bias voltage. Again, as we change the bias voltage or we increase the bias voltage, tunneling current will increase. So, we will see that we do not use very high bias voltage here. Bias voltage is around 0 to 1 volt bias voltage is used to make the current to flow in one direction. For the imaging, the bias voltage should be as high as possible to increase the tunneling current, certainly, because the tunneling current is very small in the picoampere to nanoampere. So, in order to increase the tunneling current to nanoampere or to measure without much noise with a certain signal to noise ratio, the bias voltage can be increased, but that bias voltage is again very small, 0.1 to 1 volt. By applying this bias voltage, we can measure the currents in picoampere to nanoampere level, and that can be utilized for constructing the image. And the tunneling current is nanoampere to picoampere, and this requires, certainly as the current level is very small here, tunneling current, this requires noise free superior electronics, allowing the measure such a low current. And for that we have discussed that the current amplifier is used, a very high quality current amplifier is used, which can measure the current of such a low value, and this current amplifier is placed very close to the tip and sample. And the factors to achieve atomic resolution certainly should be atomically sharp tip, and then having a 3D piezo scanner moving the tip and sample with a subatomic precision. So, that piezoelectric scanner is used to make the tip go at very small steps in a angstrom level, so that we can accurately measure how much tip has gone up or how much tip has come down. Accordingly, we can create the surface topology of the sample. Good mechanical stability, certainly we have discussed earlier before, high mechanical stability is required, because here the distance between the tip sample is very small, and vibration damping platform, and certainly low noise current amplifier that can amplify picoampere of the current, tunneling current, and allow it to monitor how it is changing across the sample surface. And how to measure the tunneling current? Since this tunneling current is very small, I said the picoampere to nanoampere, and the bias voltage applied is less than 1 volt. We normally use high feedback resistance, that is what we have discussed earlier, high feedback resistance in the at least 1 giga ohm, and the tip is normally biased to 0 volt, or it is grounded. The tip is grounded. On the other hand, bias voltage is provided to the sample from a constant voltage source. So, we provide bias to the sample either less than 0 volt or greater than 0 volt, and then measure the tunneling current passing tunneling current generated between this tip and sample. If we talk about the tunneling direction, so if two metals comes together, let us say sample and tip, they have a particular work that means work function phi 1 and phi 2. So, if they come closer, certainly the current will not pass, and then there will be no current passing from either tip to sample or sample to tip if there is no bias, if the V bias is 0, because they will align, and the Fermi level will align when they come closer to each other, and without applying a bias, current will not flow. But if we apply a bias potential, let us say we apply a negative potential to the sample, then electrons will tunnel from the sample to the tip. Electrons are tunneling from the sample to the tip, and when electron tunnel from tip to the sample, it gives the information regarding the field states of the sample, because electrons will always pass or travel, or electrons will flow from the field states of the sample or occupied states of the sample to the unoccupied states of the tip. If we apply the a negative potentials to the sample, electrons will tunnel from the sample to the tip, providing the occupied states information on occupied states, electronic states of the sample. Similarly, now if if we apply a negative potential, electrons will flow from the occupied states of the sample to the tip. Therefore, if we want to create an image, then we will find an image of occupied states of the sample or nothing but the presence of the atoms which are which have field states. If we do opposite, like if we apply a negative potential to the tip and positive potential to the sample, then electrons will tunnel from the field states of the tip to the unoccupied or unfilled states of the sample or unoccupied states of the sample. If we do the opposite, then we will see an image of the sample where the atoms are having unoccupied levels. So, the density of states, or we can know the electronic structure of the surface by choosing or by controlling the voltage applied to either tip or sample. So, here you see here what happens the tunneling direction. If there is no bias, then their Fermi level are aligned and current flows, the tunneling current do not flow in any of the direction. But if the sample is given a negative potential, then it will provide the field states of the sample or occupied states of the sample. On the other hand, if the tip is negative potential and sample is positive potential, then it provides electrons will tunnel from the tip to sample, providing the unoccupied states of the sample or the surface of the sample that we examine by the scanning tunneling microscope. In this way, it provides the surface electronic structure of the sample examined under STM. We can not only do the surface topology, but also the electronic structure of the surface atoms. More examples we will see later. And what the conclusion of the today lecture is that the tunneling current or the transmission coefficient, which is equivalent to tunneling current, which is exponentially depend on the tip sample gap between the tip sample or tip sample distance, and which is very highly sensitive. And as the current increases or decreases more than or approximately 10 times for every 1 angstrom change in the tip sample distance, we can control the moments of the tip to a subatomic level, thereby getting information high vertical resolution. In addition to that, as we are using here the tip which has a atoms single atom at its apex, therefore, we get high lateral resolution. And by applying a bias voltage, by suitable bias voltage, either positive or negative bias voltage to the sample, we can get the occupied states or unoccupied states information of the surface of the sample surface. These are the two references book for more information. Thank you.